Welcome back to Modern Algebra. We've proved the fundamental homomorphism theorem for groups, which is written here for your reference. And in this segment, we'll look at using this theorem to obtain group isomorphisms. How do you use it? It's quite a fun theorem. Once you get used to it. Because basically, as I said at the beginning, any group homomorphism will be converted by this theorem to a related group isomorphism. And so the way you use it, someone will come along and give you a function between two groups. Say f from g to k. And you might have to prove at the beginning that it really is a group homomorphism. Namely, f of a star b is f of a dot f of b for all a, b, and g. If you can do that, if you've proved it's a homomorphism, then the theorem applies. Applies to every homomorphism. I guess step 2 would be use the definition of f, which will be different from one problem to the next, to calculate the kernel and the image of f as explicitly as possible. And we have a bunch of examples of calculating kernels and so forth a few videos ago. And then you just announce, as step 3, by the fundamental homomorphism theorem, you can conclude that G mod the kernel of F, that quotient group, is isomorphic to the image of F. And there's even this formula for the isomorphism. Often we only care about the fact that there is an isomorphism, and we don't necessarily need the actual formula, although it can be useful in some cases. All right, and because we've already proved it, unless the goal is to reprove the theorem, you can use the theorem with no further explanation and get a whole bunch of isomorphisms that involve quotient groups. And again, this can help us understand what quotient groups are telling us. I talked about discarding the information in H, and again, this is going to give us a new viewpoint on that. Let's look at a bunch of examples of this process to get used to it. And the first two examples, I'll call it example A and B, might be a little bit silly, but just to get used to it and not have some complicated, formula right at the beginning. What if we looked at an arbitrary group G and took the identity map, ID sub G, not the identity element, the identity function, on the set G, where G star is any group. Well, as we may have done before, I can't remember if this was an example, this is certainly I think it was actually, this is a group homomorphism. In fact, it's an isomorphism. But it's, for using the theorem, you want to check it's a homomorphism. And in this case, it's basically immediate because the identity map just sends every input to itself. So ID of A star B is A star B, which is also ID applied to A, star ID applied to B, for any A, B, and G. And just to illustrate, I'll just reprove that to illustrate this step 1 here. And then, as I'm sure we saw when we talked about kernels and images, so I won't go through the detailed proof, the image of the identity function from G to G is the whole codomain G. And the kernel of the identity map which elements of G get sent to E by the identity function, well, just E. That E, the identity element of G. I'll say as you can check. It's almost immediate that I'm not writing the details of what I just said on the board. Okay. But in any case, having done the 3 steps, it's a homomorphism, we have the image, we have the kernel, we therefore conclude, in example A, that the particular quotient group, G/EG, is simply isomorphic to the image, which is G. So in this case, if you sort of divide out by just the subgroup that's just the identity element, that doesn't actually really do anything as far as the algebra is concerned. It's you get a group of the same size as the original group that's just G itself again, according to this isomorphism here. So because the subgroup H has only one thing in it, we didn't actually discard any information when we did the quotient group, and we still just have G, an isomorphic copy of G as that quotient group. All right, so at the other extreme, example B, once again we'll have an arbitrary group G. And this time, let's look at the function from G to G that sends everything to E. So f of x is EG for every x in the group. Everything gets sent to the identity, which is very different from what the identity function did, that sent everything to itself. Carefully contrast those two situations, and don't confuse the identity function with the identity element. All right? Well, okay, but this is also a group homomorphism. Because in this case, if you look at f of a star b, you just get E. But E is E star E, and that's equal to f of a star f of b, because f of a is E and f of b is E. All right, so it's a group homomorphism. Again, I'll omit the detailed check, but it's quite easy to check given the simple formula that the image of f consists of just E, EG, since everything maps to G, EG, that's all you get. And on the other hand, from this formula, it's also basically immediate that the kernel, the set of all x in G that go to EG is everything in G. So the kernel in this case is all of G. So by the fundamental homomorphism theorem, which FHT, if you want to use some abbreviation, what do we get out of this one? So now the kernel is G, and the domain is G. So G/G is isomorphic to the image, which is a one-element group. So that's, not very interesting, but it's showing you that when you take the quotient group G/G, you've discarded all the information. And you just get this sort of trivial little one-element group as a result. All one-element groups, of course, are isomorphic to each other. They have the same multiplication table. All right. So let's look at a more substantive example, or more interesting. I mean, these are interesting in their own way to get used to what's happening. Let's look at the determinant function on, say, 3x3 invertible matrices. So the domain then would be the group GL3 of R, let's say. And to make sure we're mapping into a group, the determinant's a real number, but it's for invertible matrices, it's never 0. So the group over here is the non-zero reals under multiplication. They're both multiplicative groups here. And all right, well, from linear algebra, we could say this relatively hard fact, but we've been using it, which is that basically that the determinant is a group homomorphism. The determinant of AB is the determinant of A times the determinant of B. And that's exactly what it means to be a group homomorphism. And all right, so here the kernel, I think this might have been an example before, but let's just remember, the kernel of the determinant map with this domain, by definition, is the set of all A in GL3 of R, such that when you do the determinant, you get the identity of this group, which is 1. And I can't remember if I used this name for it earlier, but this is given the name SL3 of R, this special linear group, if the determinant is 1. And just for convenience, I'll introduce that notation, whether or not I've used it before. Okay? There was a homework problem, actually, where you proved that this set was a normal subgroup of GL3 of R. And back in problem set 4, I think, and there you had to do all the closure properties. But now that we know about group homomorphisms, this immediately tells you that this is a normal subgroup of that group because it's the kernel of something. So that's kind of a neat sort of shortcut sometimes to showing something as a normal subgroup. You don't have to check all the closure stuff if he happens to notice this. Okay. Now, what about the image? I claim that the image of the determinant map is the entire codomain of non-zero reals, because for any such real number, if you give me, say, little r not equal 0, a real non-zero number, I can come up with some matrix, some 3x3 matrix, whose determinant is R. You could use just a diagonal matrix with R in the 1, 1 position, and then 1s on the diagonal after that, which is certainly invertible. It's diagonal, and the determinant is R. All right? So, now that we've identified the kernel in the image, we get a rather interesting quotient group isomorphism. GL3R, all invertible 3x3 matrices. If you quotient out the SL3R, the determinant 1 matrices, that weird-looking quotient group is nothing other than the group of non-zero real numbers under multiplication. Isomorphic to that group, I should say. All right, and this is one of the great things. Quotient groups are weird, and you don't want to deal with them maybe, but this maybe will convert a quotient group into something that's much more natural, this image that you already sort of understand. And what this is sort of saying, and you can think about it in two equivalent ways, the determinant takes a matrix, an invertible matrix, and discards all kinds of information about that matrix. It boils the 3x3 matrix down into a single real number, non-zero real number, called the determinant of it. It just forgets everything else. And, well, the quotient group does the same thing in a way that doesn't explicitly require the homomorphism to be in front of us. It's saying all this collection of matrices of determinant 1, this normal subgroup, we're going to, get rid of that information and discard it in some sense. And then there's not going to be very much information left. The 3x3 matrix with 9 sort of real numbers in it is boiling down to a single real number in the end. That's what this isomorphism is revealing to us about this quotient group. Okay? So there's an example. 2 more neat examples, and then we'll be done with the topic. Example D. Let's look at a function. I'll just call it f again. It's from Z13 Z3 cross Z4 product group to Z6. And it's going to take an ordered pair, AB, where A is in Z3 and B is in Z4. And it's going to just send that to 2A. That's my definition. And this is very similar to something we had before, I think, where I didn't have the B. It was just f of A equals 2A. So I'll just say can check. You can do it exhaustively, perhaps. The B doesn't really matter, so it's not as much of an exhaustion as you might think. But I'll just say can check that F really is a group homomorphism, which in this case means that F of AB plus CD is F of AB plus F of CD addition mod 6 over here for all A, B, C, D, you know, the usual stuff. Let's not belabor it. I won't go through the details of that check. But what else can you say? What's the image of F? And again, the B doesn't really matter as far as the output goes. And A can be 0, 1, or 2. So when you put that in for every B, you're always going to get 0, 1, or 2 multiplied by 2. So you're going to get 0, 2, 4, which is a subgroup of Z6, but not the whole thing. Okay? And the kernel of F. So when is this going to map to 0 in Z6? Well, basically, A has to be 0, and B can be anything. So just by directly doing it, we're going to get several ordered pairs here. We're going to get 0, 0, 0, 1, 0, 2, and 0, 3, which is a normal subgroup, because it's a kernel, of Z3 cross Z4. Also, that's Z3 cross Z4 is commutative, so it would have to be normal, no matter what. All right, and let's see. I want to draw this, but do I have enough room is the question. Do I have enough room? Let's try it. But let me draw it like this. I'll draw it in a slightly different way than before. So I'm going to draw the arrow diagram here. So we've got 0, 0, and 0, 1, 0, 2, and 0, 3. It'll be like a dot for each of those. And we've also got 1, 0, 1, 1, 1, 2, and 1, 3. And these dots represent the inputs for my arrow diagram. And then finally we've got 2, 0, 2, 1, 2, 2, and 2, 3. So this is a picture of the domain, Z3 cross Z4. Now usually you put maybe the Z3 would go sort of horizontally and Z4 would go up, but for this it's going to be nicer to draw it this way. And then over here we have the codomain, which is Z6, 0, 1, 2, 3, 4, 5. Six-element group under addition. And the neat thing is, the arrow diagram for F sort of tells you lots and lots of stuff. So like all of these things, as we just pointed out, these all go to 0. And I'm going to have a mess of arrows here. All those points go to 0. And then all the points in this row, where A is 1, go to 2. So we had this, I called it the fiber, if you remember that word. And then everything in the final third row, where A is 2, these all map to 4 under this map F. And the image over here is 0, 2, 4. There's the image. And over here, we have the kernel. The yellow guy is the kernel of F, which we often call H in my theorem just for brevity. And then everything else, this next row is a coset of the kernel. And the next row is another coset. And you can maybe clearly see now, well, maybe I didn't even write the final conclusion here, but the conclusion from the fundamental homomorphism theorem from this problem is that Z3 cross Z4 mod or quotient out by this thing, and you might notice that that thing could be written as a product set, the singleton 0 cross Z4, is isomorphic to this image group 0, 2, 4 over here, which incidentally is a cyclic group, so that's, by a different theorem, that's known to be isomorphic to the integers mod 3 by another theorem that we have. And this picture should make this a very believable statement, because it's showing you how each coset, each fiber, is mapping over to the appropriate element. And so this 3-element group is going to act exactly the same way as this 3-element quotient group. You can also almost see the fact that what's being discarded here with the quotient operation, the second coordinate is being forgotten, and then just to make it more interesting, the first coordinate, 0, 1, 2, is being multiplied by 2 to give you 0, 2, 4. Then you could just go back and divide it back by 2 to get back to Z3. But so here again we see the idea of the quotient discarding the information in the subgroup, the kernel in this case, to get a simpler group which ends up always being the image of the associated group homomorphism. All right, we'll do one more example once I erase the board. All right, so one final thrilling example of this theorem, example E. We're going to look at a function from R cross R to R. Let's call it little p, by sending the ordered pair xy, which is an input to p, to x plus y. And I'm pretty sure we checked in one of the video segments recently that this is a group homomorphism for these additive groups. Go back and review that. It's a group homomorphism. And I think we figured out the kernel, which ordered pairs x comma y map to 0. Well, it's the set of all xy such that x plus y is equal to 0, which is also known as the line y equals negative x. A line through the origin of slope minus 1. And the image, maybe we didn't do this before, but the image of P, I claim, is all of R. The entire codomain. Why? Because if you give me an R, a little r, any arbitrary little r in the reals, among many other things, you could notice that the ordered pair R0 gets sent to R, so R is in the image of P. And the image, by definition, is a subset of R, or by closure of R under addition, so that gives you the other set inclusion. All right? And anyway, so then what that means let's call this, maybe call this line L. I don't think we've used that letter yet. Just for brevity, what we can conclude from the fundamental homomorphism theorem is that taking the xy plane, this product group, R cross R, and dividing out this line in the quotient group construction just gives you R, a group isomorphic to the additive group of real numbers. So it sort of demystifies what the quotient group's doing. But that's not even the main thrust of this final example. The thing I really like about this example is the picture. It's like this picture that's kind of like an arrow diagram for the function P. The function P has as its domain the entire xy plane. So this is going to look quite different from a sort of a y equals f of x picture. This is a two-variable function with one variable coming out. And how do I want to write this? I kind of want to put the codomain, I'll put a diagonal copy of R over down here, the number line, for reasons we'll see in just a moment. And then let's have the kernel, this line y equals minus x. Goes like that. So here's, we called it L. We could have also called it y equals minus x, the kernel of P. It's a subset of the domain. It's this diagonal line. Let's just put in a few tick marks here. And the idea is everything on that diagonal line, every ordered pair that's on the yellow line, gets sent, because it's the kernel, gets sent to 0, the identity of the group over here. So I'll sort of try to indicate that like this. The map P is taking points in the plane and sending them over to this other copy of the real number line. And all those yellow points go to 0. But if you look at another line, here's the line y equals 1 minus x, or x plus y equals 1. Well, that's exactly x plus y equals 1. That's the set of all points in the plane that get sent to 1 by P. And same for 2. If you drew this line, here's the line x plus y equals 2. And all of those points on that line are the points that get mapped by P to the number 2. And so on. Whoops. I meant to use a different color. Uh-oh. Whole picture is ruined. Hopefully this will come out okay. I dare not erase it with a wet eraser. I guess I already ran out of colors. I meant to use blue. Oh well. Oh well. So this one is x plus y equals -3/2. And lo and behold, everything on that line goes to there. Here's the blue one that I meant to use. Points mapping to -1. All right, so sorry if that's a little bit messy, but the point is, what is the quotient group, R cross R over L? It's the set of all cosets of L. And all these lines that I drew, all these diagonal lines, the lines of slope -1, are precisely the cosets of L. For instance, the green line, the line x plus y equals 1, is none other than L plus 1, 0, or also known as L plus 0, 1. if you take the yellow kernel line, which is L, and move it over by 1, 0, that produces this green line. And same if you move it up to 0, 1. You translate it over, you get a coset. So here we vividly see the whole group, R cross R, being divided up into, sliced up into these cosets, which are diagonal lines, cosets of this particular subgroup L, the yellow line. And that division into cosets has meaning. It's telling you each coset, like the green one, this green coset is a set of everything in there that gets sent to 1 under the addition map. This guy is the set everything gets sent to 2. This is that guy's everything gets sent to -1, and so on. And so when we collapse out L and discard the information in L, the homomorphism reveals exactly what is being remembered and what is being forgotten. We're taking an ordered pair of 2 real numbers. The thing we're remembering, the image, if you like, is the sum of those numbers. But the 2 individual numbers themselves that lead to that sum are forgotten. We only remember their sum when we do P, or equivalently when we form the quotient map and replace each point in the xy plane by its coset, the line through that point. Okay? And again, it might seem like an awfully complicated way. Why don't you just do this? Okay? But again, in many situations, maybe you don't have the homomorphism. Maybe you only have the subgroup, and this sort of gives you a way of accomplishing this collapsing of information and getting this nicer, simpler group. And the fundamental homomorphism theorem essentially shows you exactly how that connects to what the homomorphism is doing. All right. That's it. See you later.